Okay, welcome back everyone. Today I want to wrap up what I've done last time with a few pictures. And then I want to talk about the three gravitational wave signals which have been detected by LIGO. Have you heard the news yesterday? Yesterday they announced the third detection of a gravitational wave. Okay, so that's the plan for today. Last time we talked about pulsar timing arrays. And here's a picture, now not produced just by hand on the board, but really with Mathematica for the characteristic. So this picture shows in which direction you could detect signals with which intensity. So the relevant quantity was the ratio of the distance between the pulsar and the Earth and the wavelength of the gravitational wave. And here I assumed that this ratio is 1. So that just one wavelength fits into the distance between the pulsar and us. And then you see a characteristic of this kind. So in the direction in which the wave propagates, you cannot see anything. And but the maximum is not precisely in the equatorial plane, not precisely in the plane perpendicular to that. This is because of the derivative term which we have in this in the formula for the redshift. So the characteristic is different from what we had discussed for the other gravitational wave detectors. So this is for a ratio of 1, and here's a picture for a ratio of what is it, 40? So you see, then you have more and more directions in which you have zeros of the amplitudes. Important thing is for which frequencies is this method sensitive. So for the sake of comparison, here's advanced LIGO. That's what you observe right now. So the intensity can be very low in comparison to other methods. So we can detect very weak signals, but the frequency range is limited to above 1 hertz, above 10 hertz, let's say, and in the other direction by a few kilohertz. So I said already, on this side it's bounded by shot noise, and on this side it's bounded by seismic noise, essentially. So this is advanced LIGO. Here is LISA, if it will ever be operational. So this is at a considerable lower frequencies, so something like 10 to the minus 3 hertz. And what we are now talking about, the pulsar timing arrays, they're even much further down on the axis where the frequency is plotted. They are typically in between 10 to the minus 8 and 10 to the minus 9 hertz, something like that. So IPTA, this is the International Pulsar Timing Array, which is now coming together. And SKA, that is something which does not exist yet, which will come online in a few years. That's a big array, partly in South Africa, partly in Australia. And you see this will push the sensitivity a bit down. But quite generally, the sensitivity is much lower than with these interferometric detectors. So you might ask yourself, can we expect any kind of sources in this range where this method could work with such extremely low frequencies and with such comparatively low amplitudes? Yes, there are. These are binary supermassive black holes. They are expected to be in this area. There's a cross. This is noted 3C66 something. This is a candidate for a binary supermassive black hole. So that's a thing sitting in the center of a galaxy, and there's some indication that it might be a binary black hole. And this would this would emit signals at the position marked by the cross. So this would be something for which the pulsar timing arrays would be sensitive. So that's about the only kind of sources for which we can hope that with pulsar timing arrays they could be observed. Okay, the next thing we discussed briefly was Doppler tracking with satellites. Here's the sensitivity for the experiment which was done with the Cassini spacecraft. This was a spacecraft which was sent to Saturn. And the only thing I want to point out here is the frequency range. Yeah, it's something around 10 to the minus 3 hertz. So at much higher frequencies than than the pulsar timing array method. And you see the sensitivity is, in comparison to the interferometric detectors, it's fairly low. Yeah? But nonetheless, as it doesn't cost anything, we are doing this Doppler tracking with satellites anyway. So why not looking for gravitational wave signals in the data? So this was the second thing we discussed, and the last thing we discussed last time was the idea of detecting gravitational waves with the help of electromagnetic waves. And this is this apparatus by Mike Cruz in Birmingham, which he constructed. So you see this tube. This is a waveguide. So there's an electromagnetic wave going around in this tube. It's a standing wave. And the idea is that if gravitational waves come in with the right frequency, and this must be a very, very high frequency now, with the right frequency and from the right direction, then it would produce a rotation of the polarization plane. And if the tuning of the frequency is chosen correctly, then it would work in a way that it would be a cumulative effect. Yes, so the rotation would add up. That's the idea. And you see there are two such instruments. The reason is, of course, that one looks for coincidences in both detectors to be sure that it is really a signal. So that's a somewhat eccentric idea, but from a theoretical point of view, I find it quite intriguing. And the other method, which is related to electromagnetic waves, is what BICEP2 claimed to have done. These were the B modes in the cosmic background radiation, which are actually there. So this was what BICEP2 observed. So that's a map of the sky, or part of the sky. Here's the right ascension. This is this angle in the sky, and there is the declination. This is this angle in the sky. And what is plotted is the direction of the polarization of the cosmic background radiation. So that's what was this instrument BICEP2 was measuring. And you see there's a characteristic pattern where you see a curl-like structure. Yeah? Here, for instance, there it is particularly conspicuous. And these are these famous B modes. Yeah, these things which are divergence-free, the divergence-free part of the vector field or direction field, which then represents a curl. And so these data are correct. Yeah, nobody doubts that BICEP2 really has measured these B modes, but the interpretation which they brought forward, this is no longer believed and actually was withdrawn by the authors themselves. So this has nothing to do with gravitational waves. Yeah, it is dust. It is dust which influences the cosmic background radiation. So these were a few pictures about the things we discussed last time. And to summarize this, here is one of the best known and most often copied diagram, where you see the frequency, and then there is marked what kind of sources one could observe with what kind of instruments. So the interferometric detectors are here at comparatively high frequencies, above 1 Hertz, below a few kilohertz. And what we observe with them, what we have already observed with them, is for instance, the merger of stellar black holes, heavy stellar black holes, but nonetheless not supermassive black holes. And then it goes down. Here would be LISA at lower frequencies, and the other things we have just been talking about at even lower frequencies, which then makes also, for instance, the mergers of or the spiraling motion of supermassive black holes observable. So at the moment we are here. We are here with our interferometric detectors. And now I want to talk about what actually has been observed. So we have now 3 gravitational wave signals. These are the names. So GW obviously stands for gravitational waves. So the LIGO team uses the abbreviation GW when they have convinced themselves that there really was a gravitational wave. There's a candidate, they have other abbreviations. So if something starts with a GW, then it was announced as really a gravitational wave signal. And 3 such signals have been announced. The first was measured on 14th September 2015. So you see the date. Here the numbers which follow the GW is just the date. 2015, September 09, and 14 is the day. The second one, this was a Boxing Day event, 26th of December. That's what in the UK and in the US is called the Boxing Day. And the other one was observed on 4th of January this year. And as I said, it was announced yesterday. So the paper in PRL came out yesterday. All three observations were published in PRL, public physical review letters. Here are the references. And all of them have something like 1,000 authors. Yeah? So this is a whole LIGO collaboration which is on these papers. If you are lucky enough, if your name begins with ABB, then it's fairly sure that you will be the first in the alphabet of these authors. So this gentleman by the name of Abbott is always the first author of these papers. Okay, just to remind you, the instruments which measured these signals, these were the LIGO detectors. One of them is in Hanford in Washington. The other one is in Livingston in Louisiana. That's about 3,000 kilometers apart, which means that light needs 10 milliseconds to travel this distance. So what you expect would be if a gravitational wave signal comes in. Well, if it comes exactly if the propagation direction of the wave is precisely in the direction of this connecting line, then you would expect a time delay of 10 milliseconds. Yeah? One detector would see the signal 10 milliseconds before the other one. If it comes in under a certain angle, then the time delay is smaller. If it comes in under 90 degrees, then there would be no time delay. Yeah? So whenever you see something in both detectors with a time delay of less than 10 milliseconds, then it's compatible with the idea that this was a real signal coming in from outer space. We have already talked about the instruments, how they are constructed. So these are Michelson interferometers. But whereas geometric arm length is only 4 kilometers, the effective arm length is 300 times that much, because light goes 300 times between these two mirrors before it then goes to the detector. So the effective arm length is something like 1,200 kilometers. And here's the sensitivity curve. Again, the important thing is the frequency. You see the maximum. The maximal sensitivity is at a few hundred hertz. And we will see in a minute that luckily this was exactly the frequency of the signals which were observed. They were here in this range. By the way, I think it was Tammy who last time asked what are these spikes, where are they coming from? Obviously these are some resonances. On second thought, I would guess that it is the resonance frequency of the files on which the mirrors are suspended. Yeah, these are oscillators. They have eigenfrequencies, and of course, if in the noise there are Fourier components with precisely this frequency, then they would produce these resonance effects. So that's my guess. I'm not sure if this interpretation is correct, but that's what I would guess. And you see the sensitivity, it goes down here near the highest point of sensitivity to almost 10 to the minus 3. The signal, which the first gravitational wave signal, was at 10 to the minus 21. Yeah? So it was well above the noise level. Actually, it was at a point where it could even have been barely detected by the old LIGO version, yeah, before the upgrade. So this was at this time it would have been just at the borderline. But now it was with advanced LIGO, it was really well above the noise level. Okay, so what was observed? Here's a famous picture for the first gravitational wave signal. I think everybody has seen this. So what we see plotted over time, what was observed, and the time was about 0.2 seconds. Yeah, everything happened within 0.2 seconds, 1/5 of a second. And the signal was observed in Hanford, that's the left part of the picture, and also in Livingston. Yeah, if it would have been observed only at one detector, one wouldn't have taken it seriously. Yeah? Both detectors have to act. in order to qualify as a true signal. And well, what is plotted there is is the amplitude, is the strain. So this is this quantity which we have calculated for this highly over-idealized case of two Newtonian point masses spiraling towards each other. You remember there we got this chirp signal which went up to infinity. Of course, that's not what happens for a real in-spiral. For a real in-spiral, it will go up to a certain maximum, and then it will go down again. So this final phase is what we call the ring down. And this is what you see already with the naked eye in the first panel, where the signal, well, it's not exactly the signal as it was measured, which is plotted in the first row. It is sent through a band filter, so that only those frequencies which lie in the domain of sensitivity of the detector are shown. Yeah, so this is something between 10 hertz and, I don't know, 10 kilohertz or something like that in this area. Everything else is filtered out. Yeah. So you have to be careful when you reconstruct the signal from such a plot where some frequencies have been filtered out, because they, of course, then are missing. They are missing then in the data. So this has to be taken into account when you evaluate the signal. So on the left-hand side, you see the signal as it was measured in Hanford, and on the right-hand side in blue, you see what was measured in Livingston. And on the right-hand side, you see the blue signal overlaid, but not exactly as it arrived, but rather time-shifted by, I think, 6.9 milliseconds. Yeah, something between 0 and 10 milliseconds, yeah, as it has to be. I think it was 6.9. And also, you see there it is inverted. Why do they invert the Hanford signal? Well, because the things are not oriented parallel to each other. So what's the maximum for one is the minimum for the other. Yeah, that's the reason why the signal is also inverted. But you see, if you do these two things, if you invert the signal from Hanford, and if you shift it on the time axis by 6.9 milliseconds, then they fit very nicely above each other. So the idea is that this was the same signal which came in under a certain angle. You can now calculate the angle from the time delay, and it was found in both detectors. So from the time delay, you get the angle between the direction from which the gravitational wave came and the connecting line between Hanford and Livingston. So you get a circle in the sky. Yeah? So you know that it was somewhere on this circle. Actually, because the detectors are not sensitive in all directions in space, you get not the full circle. Part of the full circle can be excluded. So what you get is a kind of banana in the sky, yeah? Where the signal should have come from. So then, what they did here is they compared the signal with, let's just concentrate on this red curve here. The red curve is something which is a computer simulation, yeah, a numerical simulation of a black hole merger with certain parameters, certain masses, certain spins, and the parameters have chosen in such a way that they fit the signal as good as possible. And you see, you can choose the parameters very nicely so that they fit the signal fairly well. And here you see what is then left, the residual. This is what you would interpret as noise. Yeah? If the interpretation is correct, if this really was a black hole merger with these masses for which the parameters have been chosen, then what is left, what must be subtracted, must be the noise. And this is this here. And the noise level is important. So you see this goes up to, I don't know, 0.3, 0.4, something like that. So everything with an amplitude smaller than that can actually not be, has actually not been measured. Yeah, it is drowned in the noise. And if you now go back to the first row, then you see that practically the entire ring down has an amplitude which is below the noise level. Yeah? So we don't really see the ring down. Yeah? One has to admit this honestly. Yeah? This is not always stressed when you read about the evaluation of the measurement, but I think that's an important point. So what we see nicely is the in-spiral, then the merger where the amplitude reaches the maximum, then it really comes out of the noise very far. So it's a true signal. There's no doubt about that. But what happens after that cannot really be told. Yeah, we know that we know about the maximal amplitude it can have, but what exactly happens in this low amplitude region, we cannot really say. So that's an important point, because now you may ask, if we don't see the ring down, why are we so sure that these are black holes? Yeah, the characteristic features which distinguish black holes from things with a surface comes with the ring down, not with the in-spiral. The in-spiral is more or less the same, whether they are surfaces or whether you have black holes with a horizon. But the ring down is characteristically different. But nonetheless, we are fairly sure that they are black holes. I will explain in a minute why we are so sure. But let's first look at the last row. This is maybe the most interesting picture. This is the frequency over time. So you see the frequency. So this is a typical chirp signal. Yeah. So the frequency increases with time. So you can interpret this very nicely when you say this is a signal with a certain frequency, but this frequency has a time dependence. And the time so it begins with something like 35 hertz, and it ends with something like, I don't know, 300 something. I think, a little bit more than 300 hertz. That's the maximum. No, wait a minute. No, it's 100. Yeah. So if we just look at the, so here's a certain uncertainty around the values. So if you just look at the central plot, then it ends near 150 hertz. Yeah. So immediately before the merger, the frequency was something like 150 hertz. I remember that the frequency of the orbit was 75 hertz. Yeah, and we always, so the frequency of the gravitational wave is a thing I denoted little omega, and the little omega was always 2 times the capital omega. Yeah, the omega with which the two things orbit each other. And this was something like 75 hertz here. So observed 150 hertz, more or less exactly at the point where the LIGO detectors are most sensitive. And you see the merger happens within something like 20 milliseconds. Yeah? And in this 20 milliseconds, all the radiation goes away, essentially all the radiation. Of course, it radiates also earlier than that a little bit, but essentially the radiation begins with a merger and happens within something like 20 milliseconds. And when we look at the numbers, we will see in a minute that what is radiated away is 3 solar masses. 3 solar masses in 20 milliseconds. That's an incredible power. Yeah? Maybe the numbers, when you see them for the first time, do not look so impressive. But this is about 50 times the power all the stars in the sky emit, in the electromagnetic spectrum. All the skies, all the stars in the sky, in all galaxies, what they emit in the electromagnetic spectrum is something like 1 over 50 of what this black hole merger emitted what these 2 black holes emitted during the merger. Okay, so why are we pretty sure that it was a merger of 2 black holes? Well, an essential quantity which you can actually read more or less directly from the picture is a so-called chirp mass. So the chirp mass is a funny combination of M1 and M2. You see there are these strange powers, but if you calculate this expression, then you see it really has a dimension of a mass. Yeah, so the powers, the units cancel out to give something with the unit of a mass. And for this funny combination of M1 and M2, you can derive from the lowest order post-Newtonian approximation, not from the Newtonian equation, which we have considered, but from the lowest order post-Newtonian equation, you can calculate a relation with the frequency. The frequency is here denoted f. That's our omega up to a factor 2 pi. And you see, if you know f and if you know f dot, f and the time derivative of f, you can calculate the chirp mass. The chirp mass is determined by f and f dot are measurable. You can read them from the diagram. So if you do this with the data from this gravitational wave signal, you find that the chirp mass is 30 solar masses. And now it's elementary algebra. If in the chirp mass you have this product M1, M2, you can estimate this with the help of the binomial formula. And then you get an inequality for M1 plus M2. And this shows that M1 plus M2 must be bigger than 70 solar masses. M1, M2 bigger than 70 solar masses. So we can forget about neutron stars. Yeah? It's impossible that this is a pair of neutron stars. But the neutron stars we know, the heaviest neutron star we know of has a mass of just a little bit over 2 solar masses. And well, from a theoretical point of view, some people believe that there might be neutron stars with a little bit more than 3 solar masses, but definitely not in the order of 70 solar masses. That's out of the question. So it's certainly not a pair of neutron stars. What about a pair of a black hole and a neutron star? Then the masses must be very different from each other. Yeah, if M1 plus M2 must be 70 solar masses, and one is a neutron star, would have something, let's be generous, let's say 5 solar masses. Yeah? But then the other one, the black hole, must have something like 65 solar masses. And now we can calculate the frequency with which such an object would merge, where one is very heavy, 65 solar masses, and the other one is a comparatively small thing. You would see that the frequency would be considerably lower than 75 hertz. You cannot have an inspiral with 75 hertz for such a heavy object. So that's the reason why most people believe this must have been a pair of black holes. Yeah? Of course, you might say maybe there are objects we just don't know about until now. So we know ordinary stars, and for the final states we know white dwarfs, which are which have totally different masses than we have here in the game, neutron stars and black holes. These are the things where we are really sure, more or less sure, that they exist in nature. But then there are exotic objects like boson stars. Nobody has ever seen a boson star. Most people believe that they don't exist. They have funny theoretical properties, but they could exist. And actually, it's not totally ruled out that this was a merger of 2 boson stars. If you believe in such exotic objects, then you may take them into account. But if we are conservative, if we believe that it was probably one of the things we already know about, that they really exist in nature, then a pair of black holes is the only possibility. That's the argument why we believe that these are black holes. Yeah? As long as we haven't really seen the ring down, we cannot be sure that we have no further evidence for this. The evidence comes only from the masses. But if we, as a working hypothesis, accept this, that this was a pair of black holes, and we calculate everything on the basis of this hypothesis, everything fits perfectly well. Perfectly well. Yeah? So this is something which gives you some confidence that this idea might be correct. So what you do is you try to fit the parameters of the black hole, the masses and the spins in such a way that the data are best fit. And what comes out is this here. So one of the black holes had, before the merger, a mass of 36 solar masses. The other one, well, this is from the original paper from February 2016. Now the mass of the second partner has gone up a little bit. What you now find in the literature is something a little bit above 30 solar masses, but that's about the order, 30 and 36, something like that. And the final black hole after the merger is 62 solar masses. So if you add these two things together and subtract it from this here, you see that there's a difference of 3 solar masses. So these 3 solar masses have been radiated away. And as I said, in something like 20 milliseconds. We are not really sure about the spin, so this has a fairly high uncertainty, but the most likely value is that the final spin is 0.67, where this is the spin is here measured in natural geometric units, which means that a spin equal 1 is an extremal black hole. That's a black hole. If you spin it up even more, then it is no longer a black hole, then it becomes a naked singularity. Yeah? So this is about 2/3 of the maximal spin a black hole can have. And the distance, we know the distance fairly sure, with fairly high certainty. Why? Well, after we have fitted all the parameters to the data, then we know the orbit. We know the orbit and we know the masses. And then we can use Einstein's formula. We use it backward. Yeah, we solve it for the distance. Yeah, the distance is then the only unknown quantity in Einstein's formula. Yeah, the power is measured. The data are known after they have been fitted, and then the distance is the only unknown quantity, which follows from the amplitude of the signal. And what you get is 410 megaparsecs. So it's well outside of our own galaxy. It's in some other galaxy, but in which galaxy we don't know. Yeah, because as I said, we have located the thing only within this big banana. If we had a third and maybe even a fourth gravitational wave detector somewhere else, then we could locate the things much better. But with only the 2 LIGO detectors, the location is not very good. So 410 megaparsecs, yeah, this is another galaxy, but which galaxy it is, we don't know.
So there are many galaxies.
Yes. Well, this area, I said it's this banana-shaped and it's fairly big. If you ask about the area where you find the source with 90% likelihood, then this is a banana which is almost as big as the constellation Orion. You have an idea how big Orion is in the sky? Yeah. So we know it's somewhere there. Yeah, that's the only information we have with a 90% likelihood. If you are satisfied with 50% or so, then it's narrower, but we don't really know where it is. Well, people started, of course, immediately looking for electromagnetic signals from the same region. Yeah, so the question was, did this event also emit some kind of electromagnetic radiation, which has been observed here on Earth? And actually, the Fermi satellite saw a very weak gamma burst within less than a millisecond. Within less than a millisecond from this gravitational wave detection. But this was not seen by other two gamma ray observers. There were 2 other satellites. One is Agile, and the other one is, what else is active? Let me forgot. Integral and Agile are the other 2 gamma ray detectors, which were active at the time and which didn't see anything. And yeah, for some time there was discussion if this could have been a gamma ray burst associated with a gravitational wave. But finally, most people came to the conclusion that it wasn't a gamma ray at all. Yeah, it was some kind of background which was detected by this instrument, as it happens just statistically. So, yeah, so because the other detectors didn't see anything, I believe now most people don't think that this was a real gamma ray burst, and let alone it was associated with this gravitational wave signal. Actually, if it really was a merger of black holes, we wouldn't expect an electromagnetic signal. Yeah? If black holes merged, usually we wouldn't expect any process which would emit a considerable amount of electromagnetic radiation. It's different for neutron stars. Neutron stars have surfaces. Yeah, and if something hits the surface, then it's quite likely that electromagnetic radiation is emitted. So when we ever see a merger of neutron stars, then we would actually also expect that we see counterparts in the electromagnetic spectrum. But for black holes, it was no surprise that we didn't see something like that. Nonetheless, there's always an intensive search for such counterparts. Yeah? As soon as LIGO detects a candidate, then an alert goes out to a big community of observers who observe with ordinary telescopes in the electromagnetic spectrum, and they are looking for signals. Oops. No, come on. They are looking for signals which could be associated with the gravitational wave signal. Of course, this will become a big issue as soon as we can locate sources with high accuracy in the sky. Yeah, when Kagra comes, Virgo is the first one which comes online very soon, then Kagra, and then maybe also the 3rd LIGO detector. Then we will have, that's in the foreseeable future, we will have 5 detectors distributed over the Earth, and then we can really locate the sources much better than nowadays. And then we know exactly where we have to look. Yeah? At the moment, we have an enormous big area in the sky where we have to search for electromagnetic signals, and that's more or less hopeless. Okay, this was the first signal announced in February 2016. And yeah, we are fairly sure that it will be awarded the Nobel Prize this year. Then the second one was a Boxing Day event. So there you see the amplitude was not as big. Yeah, so it's below 10 to the minus 21. It goes up to 0.5 times 10 to the minus 21. But the difference was that it lasted longer. It lasted longer. Yeah, that's about 1 second now. Yeah, In the other case, it was 1/5 of that. And again, it was registered in Hanford and in Livingston with a certain time delay of less than 10 milliseconds. So also in this case, people were fairly sure that this is a true gravitational wave signal. And that is the cleaned data which fits the observation best. So you see this was an in-spiral which took much longer. So in the other case, we had about 8 cycles. Yeah, in the case of the first gravitational wave signals, were 8 ups and downs before the maximum was reached. Here we have something like 55 cycles. And this is already an indication that the masses were lower. Yeah, because then the in-spiral is more, slower. Yeah, it's not so rapidly. And again, the ring down is completely drowned in the noise. Yeah, also in this case, we even more so than in the other case. We can say practically nothing about the ring down.
All those cycles, aren't they also drawn in the noise?
They come out significantly of the noise. Yes, in particular in the last phase before the in-spiral, before the merger. So as I said, there are gravitational wave candidates, which by the LIGO team are not abbreviated GW something, but they have a different abbreviation for that. And there are a couple of other, where there was one which was publicly announced, and then there were several other ones which where just the alert was sent to people who were looking for electromagnetic counterparts. And in all the other parts, the signal was so close to the noise that it didn't qualify the signal as a GW something. But here the signal to noise ratio was big enough so that the LIGO team was confident that this could be announced as a gravitational wave signal. And the masses in this case, which fit the observation best, are like this. So the masses were lower than in the other case. This is more what we expected for stellar mass black holes. Yeah? So we know these X-ray binaries since many decades, actually, since the 70s, where we observe binaries. And there's good indications that one partner is a black hole. The most famous candidate is Cygnus X1. And in all these cases, the masses were below 20 solar masses, say, typically around 15 solar masses or so. So people believed maybe there are stellar black holes with 25 solar masses, but not more than that. So this was a big surprise of the first observation of the gravitational wave signals, that the black holes were so heavy. Yeah. Above 30 solar masses, and the merged thing then even above 60 solar masses. So here, this is more in the ordinary range, what we expected for stellar mass black holes, 14 and 7.5. So the chirp mass, 8.9 solar masses, again above the level what one would expect for neutron stars. So again, we are fairly confident that this must be a pair of black holes. And the distance was in the same order. Again, a few hundred megaparsecs. The spin, as I said, the spin measurement is not so really reliable, not so reliable as the other data. So here it is, 3/4 of the maximum value. Okay, and again, there was something like in this case 1 solar mass emitted in the same order of magnitude, maybe 100 milliseconds or something like that. So not quite as powerful as the other event, but also very, very impressive. Yeah. So also this is something in the order of the power of all the stars in the sky simultaneously, what they emit in the electromagnetic spectrum. So you shouldn't be close to such an event, right? This would be really here on Earth. This is such a tiny amplitude where you need this sophisticated technology to verify that it is there. But if you are really close to this thing, then this would be extremely dramatic. Yeah? So these are really the most powerful, by far the most powerful events in the universe we have ever heard of. Yeah? Before the detection of these gravitational waves, we used to say that gamma ray bursts are the most powerful events in the universe. But a gamma ray burst is a puff in comparison to such a thing. Yeah? It's a completely different order of magnitude. Okay, this was the second. And then we have here's the frequency for the, no, this is the third one. This is the one which was announced yesterday. I read the paper overnight. So here you see again the frequency. In this case, it is nicer than in the preceding one. Here, actually, yeah, you don't really see the chirp so clearly as for the first event, and also as for the third event. So you see that there is a chirp, but it's not as clearly as for the first event. But now, what was announced yesterday, again, we see a very nice chirp. Oops, here it is. So. And in both detectors, the frequency goes up. So the frequency goes up to something like 200 something hertz. So the frequency of the orbital motion is something like 100 hertz, very similar to the first event. Yeah, and here is the amplitude over time. So in red, the signal as it arrived in Hanford, in blue as it arrived in Livingston, and in black the theoretical model which fits observation best. And if you fit the data to the theoretical prediction, what is then left, this is plotted here, this is interpreted as noise. And you see again, the noise level is something like 0.3, 0.4 or so. And you see the ring down is more or less in the noise. Okay, for this event yesterday, the masses were in between the other two events. So the masses were, one was again 30 solar mass, the other one about 20. So again, you can forget about neutron stars. Absolutely clear that this cannot be a neutron star. And as distance was bigger, it was farther away, about twice as far away as the Boxing Day event. Radiated energy here also in between, right? The first one was 3 solar masses, the second one was 1 solar mass, now it's about 2 solar masses. And we expect that this was not the last gravitational wave signal we have seen, right? So in English, one used to say 2 signals may be a coincidence, 3 signals is a pattern, and now we see the pattern. Yeah? We see the pattern clearly. And it was not the fact that there are gravitational waves. This was absolutely no surprise. Everyone believed this, everyone in the field, except maybe a few very eccentric persons. But this was absolutely no surprise. But there were surprises associated with this discovery. First of all, now we have 3 black hole mergers, still not a single neutron star merger. Yeah? Actually, most people would have expected that we would see neutron star mergers, maybe even more frequently than black hole mergers. Neutron star mergers, and of course, in our galaxy, in our own galaxy, most probably. This was the first thing which was not expected. And the second thing is that black holes exist in this mass range. Yeah? We believed, we are fairly sure that there are stellar mass black holes, say between 1 solar mass and 25 solar masses or so. We also believed that there are supermassive black holes with millions or billions of solar masses. Now it seems as if black holes with something between 50 and 100 solar masses are not so unusual. This also was a surprise. There was even speculation that this might give a new flavor to the dark matter debate. There was a suggestion. One of the authors was a Nobel Prize winner, Adam Rees. There was a suggestion that maybe dark matter may consist of this kind of black holes. And then a big debate started if they could really escape the methods by which black holes had been thought to be ruled out, in particular microlensing. Yeah? By microlensing, the lensing effect onto stars which pass behind a dark object, and the light is focused towards us and we see a light curve. This is routinely done. And if there were black holes around, many black holes, they would make such microlensing events. But there are some indications that the analysis in the way it has been done didn't take black holes in this mass range into account. Yeah? That if they are frequent, if black holes between 50 and 100 solar masses are frequent, then it could be that they would change this likelihood for black holes in the universe, which have been calculated from microlensing. And then maybe the dark matter debate could find a very surprising answer by in the way that in fact it is black holes. Actually, I have serious doubts that this is true, but it has now come again seriously into the debate. Yeah? So black holes for many years were actually ruled out as candidates for dark matter. Now they are in the debate again. I think that much one has to admit. Okay, so there were a few surprises associated with these observations, and of course the perspective, the most interesting perspective of all this is that it is the beginning of a gravitational wave astronomy. Yeah? That we can really use these things for these gravitational wave detectors for observing objects in a way which would not have been possible with in the electromagnetic spectrum. Yeah, about these mergers of black holes, we would never have learned with the help of telescopes in the electromagnetic spectrum, because most likely there was no electromagnetic radiation associated with them. Yeah? So we would, as it is often said, we have now a second eye for observing the universe. Of course, this will gradually develop, and I'm not sure how far it will develop during my lifetime. But it certainly, it certainly will open a new kind of astronomy. Yeah, it will have an even bigger influence than the development of radio astronomy. Yeah, when in addition to the optical telescopes, the radio telescopes were invented. This, of course, also was a big, excuse me, a big change, a big improvement. But I think this might be even more dramatic. So that's a perspective. And we expect gravitational wave observations now to become really a routine. Yeah? In particular, when the other detectors are online, then we will have something like 1,000 observations per year. That's the estimate for the year 2020, which I've read recently. And I think this is not unrealistic. Okay, so much for the observational side of the topic, and now for the rest of the term, I will then come back to theory, to calculations on the board, and we will leave this formalism where we just linearize about Minkowski space, which in a sense destroys essential aspects of the theory. Einstein's theory has something to do with curved geometries, and on these curved geometries we have these waves, and they behave quite differently from waves on flat space-time. And in the last 4 weeks or so, I will now talk about gravitational wave theory, really in the formalism we want beyond this linearized formalism. So in the next week, I will begin with gravitational waves on the Schwarzschild background. This will give us a famous Regge-Wheeler equation, which I will discuss in some detail. And after that, I will discuss some exact solutions, wave-like solutions to Einstein's field equation. So that's the plan for the last 4 weeks or so. Okay, now I say goodbye to everybody who is watching, and we continue with the tutorials. Bye-bye.